chair of the Northwest branch of the IMA, and I'm delighted to say that today we have Elysia Barker from MMU, who will be giving a presentation on the use of fractals in modelling flash floods. I think that was the title. Oh, you can put the title up. Okay, Elysia, if you'd like to put your title slide up, and I will mute myself, and we'll fractals to approximate real riverbeds. Sorry, that's it. Okay, so the title of the talk is using fractals to approximate real riverbeds. So I'll hand over to Elysia, and away you go, Elysia.
Okay. Hi, welcome to my talk. I'm going to be walking you through the ideas and inspirations, methods and development of my research and what it's expanded into. The title is Using Fractals to Approximate Real Riverbeds. So I would like to start with a bit of background. Can't change the slide. It's not letting me change the slide. Oh dear. I'd like to start with a bit of background. I began my undergraduate degree in mathematics at MMU in September 2018. At the end of my first year of the undergraduate degree, I participated in a scheme called the Third Term Scheme. For this, I worked closely with who's now my supervisor, Dr. Janjo, and I began doing my own research to create a piece of software. Upon the completion of this, I was invited to give a talk at the inaugural International Symposium on Water Modelling in Beijing, China, in July of 2019. I published a paper at the conference entitled A Python-based Graphical User Interface for a Lattice-Boltzmann method solving shallow water equations. You can see me in the picture at the yellow arrow. Currently, I'm in the second year of my PhD, at the beginning of the second year of my PhD. I specialize in computational hydrodynamics. This morning, as if in great timing, I was actually accepted to speak at a conference in Kitakyushu, Japan, this coming April, and will be publishing a paper through the conference entitled The Use of Fractional Brownian Motion in the Generation of Realistic Bed Topography, coupled with the Lattice-Boltzmann method. I think someone's not muted. It's okay. It's okay.
Menaz, could you please mute your microphone?
To begin, I would like to discuss the aims and objectives of this talk. I would like to briefly explain fractals and their importance both in mathematics and nature, and why they're important in my research currently. I would like to discuss how fractals can be used for bed generation, and how I've incorporated them in this project. I'm then going to discuss the methods that I've chosen to use to describe my project. I'll also show you some simulations I've run using the Lattice-Boltzmann method, which is a method of simulating shallow water equations over both the generated topography that I've created and over real topography taken from a specific paper, which I will also share. I'm then going to explain the supporting results for my method and how I am going to take this method, how I'm going to continue research in this method going forwards. I intend to use this method in the creation of an overall method to model flash flooding. I'm hoping to call this the Lattice-Boltzmann method for flash flooding, which is the ideal outcome of my PhD, which will be to create a new method of modeling flash flooding more accurate than what is currently exists. So I would first like to begin by introducing you to a concept I'm sure most of you are aware of. Fractals. Fractals are incredibly interesting and have powerful properties which can be applied in many different areas across any subject you can think of. Art, science, maths, and architecture are just a few examples. Fractals, generally speaking, are a series of simple instructions repeated infinitely and creating a recursive loop. So if you have an image of a fractal, no matter where you zoom into it, it will look the same, no matter how far the zoom. To give you a brief idea of an example of a fractal, I'll introduce you to the Cantor set. It was first discovered or created by a German mathematician, George Cantor. He was also very involved in the creation of set theory. Fractal consists of a straight line as its initial state, which is then divided into thirds. The middle third is removed, leaving two sections, each of a third of the length of the original. This process is then repeated again with the smaller line segments, and then again, and then again, and again. No matter how, when you zoom in, no matter how far you zoom into the fractal, it will result in an image identical to that if you'd never zoomed in at all. Fractals appear all over the place in mathematics and in nature. To briefly give examples of fractals in mathematics, here are several pictures. First, we have the fractal tree. This particular one has a similar structure to broccoli. We can see the initial trunk and then bifurcating smaller trunks, which each have their own bifurcating smaller branches, and so on. The next picture is of a well-known fractal, the Mandelbrot set. This fractal, in the complex plane, the pattern indicates where the complex numbers which satisfy a specific function do not diverge to infinity. The gradient of different colors also indicates how long it takes for specific complex numbers to diverge to infinity. This next picture shows a Sierpinski style fractal. The most common of the Sierpinski fractals is the Sierpinski triangle, which can be generated in several different ways. But here we see the Sierpinski star. This next picture shows a series of simple repeating trifurcating lines which form a leaf-like shape. This behaves similarly to the fractal tree. And we can see when we zoom in to one of the strands coming out, it looks like a picture of the overall, the full image, as if we hadn't zoomed in at all. This is the Sierpinski triangle, the most common form of the Sierpinski fractal. And here we see the Koch curve from stages 1 to 5, with 1 being the most simple stage on the right, and 5 being the most complex on the left. And you can see as the fractal dimension increases, it becomes more and more detailed. And it also becomes more snowflake-like. This next picture is of a deep zoom into the Mandelbrot set. And finally, we have an image of a three-dimensional model of a Sierpinski cube, which can actually be created using pieces of card or even bus tickets if you have enough of them. We can see that fractals in mathematics are vast and varied, with these being only a few examples of an infinitely complex and interesting subject. What's more interesting is we can see these naturally occurring in the world around us. You will have unknowingly seen many fractal structures just in your own garden. Fractals in nature are a vital aspect of learning how to understand the world around us and how it works. Once I show you these examples, you'll see why I've chosen to use fractals within my research of riverbeds and fluid flow. Our first example of a fractal in nature is a tree. When we see a tree, we're reminded of the fractal tree or even the fractal leaf on the previous slide. We have a series of lines bifurcating or trifurcating, splitting off at different angles and reducing in thickness with each of the branches that grow out from the trunk. With our next example, this isn't as obvious as to what it is, but it's a succulent. And the leaves spiral from the inside outwards, getting bigger and bigger. Next, this is something more relevant to the overall topic at hand. These are a series of rivers branching out from an initial larger river, and this fractal is similar to that of a fractal tree with smaller rivers branching off from larger river. Next, we see inside of our lungs, the chambers inside of our lungs bifurcate or trifurcate off into different smaller sections. This image shows a coastline with rivers branching off into the land, something similar to the picture of the rivers. And here may be the most obvious of the fractals. This is a leaf. We can see the fractal structure, and we created this in an almost identical fashion on the previous slide, just by inputting a very, very simple series of lines of code in Python. This next one is a cabbage. Again, we see a small spiral pattern. Next, we have lightning. Lightning behaves in similar ways to rivers or trees, and the lightning bolts bifurcate and trifurcate. And also, neurons in your brain send signals in structures like lightning too. And just to round it off, here is a cross-sectional piece of broccoli, which we saw generated on the previous page. It was the first picture in yellow and orange. Now we see these fractals, and they might appear slightly different to the fractals on the previous slide, but that's because fractals in mathematics that we can generate on a computer are idealized fractals, whereas in nature there are always elements of chaos or some form of interruption. So sometimes they will look slightly different than a computer generated fractal. Fractals appear everywhere. Next time you go for a walk, look up at the tallest tree and follow it up. Take note of whether the branches bifurcate or trifurcate, and think about how the branches begin to get thinner as they grow further away from the trunk, and see how many iterations or fractal dimensions you can count the branches to. With this background in mind, I want to begin with a few concepts I'd like for you to keep in mind as we go forwards throughout the course of this talk. The first thing to bear in mind is that fractals appear everywhere, all around us, in everyday life constantly. The next thing to keep in mind is that fractals, being the complex structures they are infinite, and as a result, infinitely complex and detailed right down to the nanometer and beyond. Consider the snowflake fractal from the slide previously. The fractal becomes more and more detailed as we advance the fractal dimensions. This is how detailed the fractal is. The final thing to keep in mind is that the ground itself is far more complex than a smooth, flat surface. In fact, surfaces that appear smooth and flat are actually far more complex than they seem. For example, consider a billiard ball. Under a microscope, they don't look anywhere near as smooth as they do without any magnification. It's far more textured and rougher than we actually think. I'm sure most of you have heard of the theory that if a billiard ball was blown up to the size of the Earth, it would have mountains bigger than Everest, or likewise, if Earth was the size of a billiard ball, it would be smoother. There is some validity in this, in that obviously a billiard ball would have mountains if it was the size of the Earth, and the Earth would be incredibly smooth, like a billiard ball, if it was the size of one. Nature in the natural world is chaotic. Its ingrained characteristics are unpredictable and uncontrollable in ways that are far more complex than we can go into today. From the way water moves and behaves to the geometry of mountains or the patterns we find in trees, everything contains elements of chaos and nonlinearity. So this led me to thinking, is there more in common between chaos and natural phenomena than I originally thought? Many areas of research have implemented the use of chaos theory and fractal geometry already, including research into the behavior of water. But I was fascinated by this idea and began thinking not just about the way water behaves, but how the surface the water interacts with affects the behavior of the water itself. I began forming the early stages of a method which uses fractals to more accurately model real-world riverbeds to see if the impact this would have on the behavior of water is important to simulations themselves. My idea grew and became more ambitious as I began my research into the area. I decided I wanted to create a method which would use fractals to artificially create a bed, which is so close to real life, the changes in behavior compared to the real world would be almost negligible. I wanted to find a way to generate this topography without the need for comparing it against the real world, and which would enable us to have an extremely accurate estimate for comparing it against the real world, which otherwise we wouldn't be able to have any data. Areas of the ground we don't have any data on for one reason or another would now have data artificially created accurately. In cases where we had data available, the method would be more detailed and provide more data at a much more intricate scale. The questions you may be asking now is how, and obviously why would I want to do that? The first step is to find a way to use fractals to generate any topography. This was a relatively simple step in the process compared to the rest of it. I began looking at video games. Creators of video games often use fractal geometry to procedurally generate a realistic looking landscape. This method can create a vast amount of ground of all kinds of shapes and sizes with a relatively small amount of effort. This is how the terrain in Skyrim, Grand Theft Auto, and even Minecraft were generated, and many other games. It's far easier to write a simple set of instructions once and have the ground be generated for you, rather than to create every single pixel by hand, which would take up far more storage and time than is necessary or given in terms of if you have a time constraint. Throughout my search for finding the best method to generate fractal terrain, I found fractional Brownian motion. Brownian motion can be thought of as a process similar to diffusion. We picture particles moving randomly from an area of high concentration to low concentration independently of one another. Brownian motion, however, doesn't require a concentration gradient, but it still stands that the particles move independently of one another in an erratic and uncontrolled way, caused by the constant collision with other erratically moving particles. This can be generated using a very simple set of instructions in Python or MATLAB or whatever programming language you'd like to use. Fractional Brownian motion, or fractal Brownian motion, as it can be referred to, is a generalization of Brownian motion, in which the particles move erratically, but need not be independent of one another. Particles in the fractional Brownian motion process will behave according to the trend of the previous particles, but still in an unpredictable manner. This is what we can use to form the basis of the method. The most useful thing about fractional Brownian motion is that it has a very easy to control and desirable quality called a Hurst parameter. We discussed earlier about the fractal dimensions of the Koch snowflake being more detailed as the fractal dimensions increase. Imagine the Hurst parameter in a similar way, except the Hurst parameter describes the raggedness of the ground. The Hurst parameter must be between 0 and 1, and as the parameter gets closer to 1, the motion becomes less ragged. We can see here the graphs of the Hurst parameters between 0 and 1 in increments of 0.1, which shows clearly how ragged the motion is as it gets closer to 0. These are just general beds with nothing extra applied to them, just a general fractional Brownian motion process. Just to give an example of how important and the effect the Hurst parameter has on the actual motion in total. An example of the raggedness is this computer-generated mountain landscape using fractional Brownian motion. The images depict the same mountain region, however, the picture on the left is smoother than the picture on the right, and that's due to the Hurst parameter. I wanted to use this idea of a Hurst parameter and figure out a way to relate it to the real world. So I began running some tests, comparing the data from real beds to a generic fractional Brownian motion in order to find an average for the Hurst parameter of the ground. Here is a close-up image of the surface of one particular real bed, the River Cole in Birmingham. This is taken from a paper, which I have embedded a link to in this slide. This is only a 62-meter stretch of river. And bear in mind, this is a close-up image of the riverbed. And if we were looking at it from a distance, the drastic differences in heights would look flat, given the difference between the lowest and the highest point is not even a meter, while the stretch of riverbed is 62 meters in length. We can see the typical qualities of this riverbed, with it being 62 meters long and an average of about 97.92 meters above sea level. This is also two-dimensional, which is crucial as the method we use to simulate shallow water flows requires only a two-dimensional surface. In this 62-meter stretch of river, we only have 62 points. This means the measurements have been taken 1 point every meter. This misses so much vital information in between the points. So even though we do have a rough estimate of the real riverbed, it still isn't anywhere near as close to real life as it should be for accurate solutions. There are so many vital pieces of information missing. This is why I wanted to create a method to fill in the blanks, the unknowns, the missing details of whatever we needed. To do this, I wanted to find the raggedness parameter, the Hurst parameter, closest to real life so I can replicate the missing pieces of information as accurately as possible. In the early stages of development, I decided to use this real riverbed as a test. I would create my method, use it to simulate this as closely as possible, and compare the differences in flow results using a simple lattice-Boltzmann method program for shallow water flows. I wanted to use this real riverbed just as a single riverbed because I wanted to get the method correct first before testing it in other ways. In these initial stages, I did rely heavily on comparison of the generated bed and the real bed at several stages in the computations, which in the long run would mean my overall goals of the method would not be met, as I wouldn't be able to generate data for beds that we have no real information for if my computations relied on comparison. So this is something I kept in the back of my mind until I developed a solid structure of what I wanted to do. By using the real data to compare against, I was effectively taking a brute force technique, which was not as efficient a way to get the best results. I think I messed up the order of this, sorry. To make things easier on myself, I decided to effectively remove the surface, the top layer of the real river and focus on that rather than the 97.5 meters below ground. Essentially, I pretended as though the lowest point of the river on the graph was at sea level, at 0, which made for far easier computations, and then the data can be raised back up to its original position once the bed has actually been determined. Early on, the Hurst parameter I found to be best fitting to the situation was 0.6. I then had to decide how detailed I wanted my results to be in comparison to the real bed data I was comparing against. Fortunately, the program I mentioned previously, which uses a lattice-Boltzmann method for shallow water flows, can be altered to use more data points per section of ground. This means that I'm able to adjust how many data points I can input into the program. For the real bed data, I have only 62 points for 62 meters. For the generated bed, I wanted to use 10 times the amount of points, so I could adjust the parameters in the program to use 620 points per 62 meters. I decided to begin by generating a bed 10 times more detailed. So my early stage brute force method could cope with this. I calculated the error between the real and generated beds for every 10th point of the generated bed. And if it exceeded a certain threshold, the program would loop back to the beginning and generate a new bed, and so on until eventually a bed was left which satisfied the criteria of being below the certain percentage difference than the real bed. This is a brute force technique, which again is not very efficient. To highlight the importance of selecting the appropriate Hurst parameter, I decided to time how long the program would take when using the Hurst parameter I selected, 0.6, and comparing it against the Hurst parameter of 0.9. The time difference between the two was baffling. I changed the thresholds of the program and measured the time taken and discovered a vast difference in the speed at which the program ultimately found its solution. With the Hurst parameter of 0.6 being more than twice as fast. Here we see a graph of 0.6 against 0.9, which shows the time taken for 3 different threshold values: 17%, 20%, and 25%. This means that if the program found the bed data to have a difference above those threshold values, it would start again. Clearly, it shows the Hurst parameter of 0.9 taking a lot longer than the Hurst parameter of 0.6. However, at the thresholds this large, the runtime is fairly short anyway. Upon further reduction of the thresholds to 15% for both 0.6 and 0.9, they skyrocketed in runtime to over 400 seconds. And even further reduction to 10% resulted in a runtime anywhere beyond 3,000 or 5,000 seconds, which is clearly not ideal, given you're waiting hours for the results to compile just for a generated bed. I needed to make it better, in other words. Initially, the results were promising and heading in the right direction, but running the program itself was taking a lot of time, and the appearance of an appropriate bed was unpredictable in the time it took, particularly when reducing the constraints further to be more specific. To overcome the extreme runtimes of the program, I decided to be more general with the constraints. So instead of restarting the program if any individual data point exceeded the threshold values, I would take the average error between all the data points, which may not have been the best idea. If that was above the threshold that I decided, it would restart the program. While this did reduce the runtime, the generated beds were not as reliable as the previous, and occasionally had enormous differences, which the program overlooked as the average still fell below the threshold. This can clearly be seen on this graph, which shows the real bed data in blue and the generated bed data in red. We can see the red line has a large peak right in the center, which deviated greatly from the real bed. Also, at the end of the bed as well, we see a huge separation between the real and the generated. We see the issues here, but the method itself overlooked them. The question at that point was how to teach the method what to look out for, how not to rely so heavily on the real data, and how to reduce the runtime even further. The key to this was the way in which we generated the bed data and the way it's handled, and the way the data is handled. Instead of comparing the data to the real bed itself, I rewrote the program so the data would be compared against itself instead of comparing it to a real data. Therefore, it no longer required any real data in order to generate a bed. How does that work? At the beginning of the program, before anything else begins, the program can take one of two routes. One, if real data exists, and another, if there is no real data at all. If real data exists, it's manually entered into a text file, which the program will read in order to make this decision. If there is no data in that text file, obviously the program will choose route 2. If real data exists, the program will complete a series of instructions to calculate certain parameters required throughout. First, it will count the number of data points and multiply it by 10, so we have 10 times as many points for the generated bed. We can increase this value to become more detailed if we want to, but at the moment I have set it to be 10 times as detailed. Then it will calculate the maximum difference between the lowest and the highest point of the real data. This is for steepness of the graph, or steepness of the bed, and it will also take the difference between each individual point. After this, it looks at the trend of any data points and decides whether the bed is inclining or declining, so going uphill or downhill. And the negative number meaning the bed will be declining, going downhill, and a positive number meaning the bed is inclining uphill. Then finally, the program will calculate the optimal Hurst parameter for that particular bed, which is a function that I've written as a separate program, which this full program calls. Route 2 is if real data doesn't exist. The parameters we discussed above are found in different ways. Each of the parameters can be manually altered to suit the kind of terrain the user requires. I've programmed the number of data points to automatically be 620, since I've been using the 62-meter real river data. And I wanted to go through route 2 rather than route 1, so that I can see if my program does work when real data doesn't exist. This also can be changed if the user knows how long the stretch of river is. If they want to use a 50-meter stretch of river, they can put in 50 meters, which will output 500 data points. Furthermore, the maximum difference between the lowest and the highest point is preset. So this will be how steep this is. I believe that I've set this to about 1.2 meters, because I don't want the steepness to be I don't want the data to be very steep. Similarly, for the differences between each individual data point, I cap this so this is able to tell the method to discount any excessively large peaks and troughs in the data. After this, the trend of the data is preset, which I preset to -1, given that the real bed that I am comparing against is on a decline, a very, very gradual downhill slope. Then finally, the Hurst parameter I have preset to 0.6, as that's an average that I have calculated based on numerous comparisons against real topographies. Again, all of these preset parameters can be changed to adapt the specifications of the user and the terrain itself. The program then continues in the following steps. Using fractional Brownian motion, a series of data points are generated, which are orientated the correct way to either be uphill or downhill, depending on the specification of the user or the real topography which has been input into the program. The constraints are then applied to the data by using the differences between both the maximum values and the minimum values, and then each value independently. This is an important step in the process, as this ensures that there are no extreme peaks like the previous version of the method allowed, and it gives the method an idea of how steep the incline is, or decline. The larger the difference between the maximum and the minimum values, the steeper the incline or decline. Similarly, the smaller the difference, obviously the less steep the incline or decline. Following from that, the method will then look at the individual points between them. And this is set at a cap so that the individual points cannot ever be more than, I have preset it to 0.6, which is 60 centimeters. So they can't be higher than 0.6 meters. So this avoids any excessive peaks and troughs. After that, it will double check the data to make sure that it satisfies all of these constraints and also doesn't deviate too far from an acceptable bed. This means excessive peaks and troughs. After that, if it's decided the bed is correct, it will output the bed as a graph on MATLAB, which I'm using MATLAB at the moment. It will output it on a graph. It will output the data points into a text file, which will be then input into the lattice Boltzmann method program, which is also on MATLAB. Additionally to that, if there is a series of real data that does exist that was initially input, the program will automatically output the percentage difference between the real bed and the generated bed, so we can see how different it is initially. Obviously, if no data exists, it doesn't, because we have nothing to compare it against. This methodology has vastly improved both the accuracy and the runtime of the program, with an average runtime of only 30 seconds down from 3,000, which is incredible. Furthermore, we can clearly see the similarities between the real bed, shown here in red, and the generated bed using the current version of my method, seen here in blue. We can see the red line, the real bed data, is smoother and less detailed, while the blue line, the generated bed, is much more textured and detailed, while following the overall trend of the original bed data, which is the ideal outcome. This generated bed data on the graph was run using route 2, described above, or before, for when no bed data was available at all. I wanted to test this, as I previously mentioned. So I input my specifications, which included a downhill trend, or a negative number for that particular parameter, a very small min-max difference of 0.6, which meant the decline was not steep at all, a small difference between each individual point, which I specified to be 0.25 meters, which is 25 centimeters, so it's slightly different than what I mentioned before. I also used the preset Hurst parameter of 0.6. After the program has output these results, I compared the generated result against the real data on a graph together, which you can see here. I believe these results to be quite successful, and the method is actually now capable of finding extremely accurate solutions without the need for any real data at all. You can see visually that this looks very similar, and hopefully in time the results will be even more similar. Now the real test is to see how the water of the river will interact with the ground and how accurately the method has simulated the topography compared to real life. The results of the method itself may appear promising, but if the simulations of the fluid over the beds are inaccurate, then the method is no good. Earlier, I mentioned using a simple lattice Boltzmann program to simulate the shallow water flows. This method is a relatively new method in computational fluid dynamics, with its inception being only in 1973. This method aims to be as simple as possible by reducing the complexity of a three-dimensional description of a fluid to a two-dimensional representation. To briefly describe how the lattice Boltzmann method simulates fluid flow, let's go. Sorry, I don't know what happened there. To briefly describe how the lattice Boltzmann method simulates fluid flow, we imagine the fluid as a two-dimensional lattice of particles. Each of the particles can move in any one of 9 possible directions. We can see there are 8 arrows around, and then the center, and then the 9th direction is stationary. This is called a 9-speed square lattice and denoted by D2Q9 for two-dimensional 9 directions. This is done on a microscopic level, so that when looked at from a macroscopic level, the particles describe the correct average movement of the fluid. This is an example of the product of the simulations. It's a graph of velocity vectors which describe how the fluid is moving and in what direction. Additionally to this, graphs of the water depth and the rate of flow or discharge can be produced. Now, with that background of the lattice Boltzmann method, I have used both the real bed data and the generated bed data in this program to run simulations of fluids. I've tested each of these beds using the most basic case, which all methods should pass, the stationary flow case, meaning there's no movement to the flow, there's no change in depth, no change in flow rates, and no change in velocity. Both the real and generated beds gave identical results. Here we see the graphs of the water depth being the left, the discharge or the flow rate in the middle, and the velocity vectors on the right. The top line being the fractional Brownian motion generated beds, and the bottom being the real beds. We can see a completely flat line for both the real and generated beds on the water depth, which is expected because there's no change in water depth. We can also see this on the graph of the discharge, which again is expected. On the velocity vectors graph, which is the one on the right, we do see something that can be mistaken as velocity. However, upon looking closer into it, the velocity shown in this graph is so small it's completely negligible, because it is 10 to the minus 17 meters per second, which is nothing. Here, I've created animations of the velocity vectors of the fluid to make viewing easier. The animation shows the first 1,000 time steps or iterations of the fluid. The flow case is slightly different to a stationary flow, but it's still a very simple basic flow case. This is a steady flow case and should continue at a steady rate. Here we can see the animations side by side in comparison. They're quite similar with some differences throughout the 1,000 time steps. Time steps are the measurement of time using this method. We can also see here the graphs again of the water depth and of the discharge in both the real and the generated beds. We see no differences between the water depth and only slight differences in the discharge, which shows promising results, but we need to look at the data produced closer. Upon further investigation, the velocity results of the real compared with the generated bed show only an 18.14% difference, which is incredible, given that only slight changes in topography can have vast impacts on the outcome. The differences in water depth is only 0.22%, which is again incredible. That's less than 1% difference. And the differences in discharge is 10.66%. Remember, the real bed in this scenario is only 62 points, so that wouldn't be as close to real life as we'd like. So that lacks many details of the actual landscape of the real bed. Further investigation will be carried out with more real beds, more data points, different kinds of beds, and then compared against the real world, as well as the bed data collected for that area. The method as a whole is showing extremely promising results, with and will only continue to develop and be more accurate and useful as time goes on. With this method, artificial beds can be created close to real life, and we will be able to give more detail closer to real life simulations than ever before. This could advance the field of hydrodynamics even further and become crucial in the future. Of course, more testing of this method will need to take place, and my hope is that this helps as many people and the areas of this research as possible. We've discussed fractals and their importance in nature, mathematics, research, and beyond. We discussed the fractional Brownian motion and its properties, how I've adapted it. We've seen the development from the early stages to the current stage of this method. We talked about the lattice-Boltzmann method. We've seen how the fluid behaves over the generated bed and compared it to the real bed. And we've seen the results showing promising outcome. For further research, the method will be applied to more complex real data and further simulations with more complex flows. Eventually, the method will be used in the creation of the overall objective of my PhD, which is to create a new method for modeling flash floods. I'm hoping to title the lattice-Boltzmann method for flash flooding, or LBMFF, which will have bed generation program built into the final product for improved accuracy. From the beginning stages of an idea being formulated to a fully working solution. I hope you've enjoyed my talk. Thank you.
Thank you, Elysia. That was fantastic. Perfect timing. So we do have 5 or 10 minutes for questions. So if anybody would like to put a question into the chat window, or if you want to unmute yourself and talk to Elysia, then please do so now. So if anybody wants to put a quick question in the chat, I could read it out, or you are welcome to unmute yourself and ask a question.
Gillian's coming.
Hello, Stephen. My name's Paul Kimber from DSTL. Very interesting talk. Some nice graphics there. In terms of flash flooding, And one of the issues, of course, is not just the water flow, but the embedded solids and other things. How do you think you might model the, if you like, a different viscosity liquid?
That is a good question. I will be, in the early stages of my method for lattice Boltzmann method of flash flooding, I will be just using water initially. And that is going to be the method I'm going to create for my flash flood, my PhD. I'm going to just use water. However, I do aim to continue research after my PhD in this specific area to incorporate sediment flow and the sediment buildup inside the water, which will increase obviously viscosity and increase the friction, and obviously change the way the water will move entirely, which will be more accurate for flash flooding, obviously, because a flash flooding by its nature does drag in all kinds of bits and boulders, trees, houses. So I will be incorporating that eventually. At this current stage, though, I will just be using water as an initial in my initial method.
Okay, thank you.
Thank you, Paul. As your question, you can unmute yourself. No, so the question is, are any geographical companies interested in using this tech, or are you yourself interested in selling this out to environmental agencies? So is the research, are any environmental agencies involved with the research, Elysia?
No, currently the research is mine and I'm working independently, just myself. I do hope one day to collaborate with different companies, and that's actually a very good point. I may reach out to some even in the near future, because that would very much help my research, especially if I could get extra funding. But at the moment, it is just me.
Okay, thank you, Elysia. Killian, you say somebody from the Learning Studio would like to ask a question. Do you want to unmute yourself?
Hi, it's Malcolm. I just wanted to ask, have you thought or considered a way of incorporating real data into your model, rather than you spoke about the runtime of running something that would look similar to something real, but is there, have you considered a way of incorporating the actual measurements into the simulation?
Yeah, so I can put real data into the simulation already. That is possible. However, the actual outcome, or the aim of the method was to create bed topography or data when we don't really have any data currently existing for whatever reason. Like, to give an example, there may be a flash flood in Iceland because there's a glacier on top of a volcano. The volcano will erupt and it might change the bed topography underneath it. So we might not have data currently at that exact for that exact bed topography anymore, because the lava flow and the fast heating of the lava into more rock may change the bed topography. So the idea was to create a method that can create bed topography accurately, close to real life, from nothing. So I can use real data, and often I do use real data for more simulations and other simulations for fluid flow using the lattice Boltzmann method. But for areas where we don't have data for whatever reason, or the data is not as detailed as we'd like, because we haven't measured that, we don't have a way to measure it, just for whatever reason, we can just press a button and it'll do it for us in a very accurate way.
Yeah, thank you, Elysia. Thank you, Malcolm. Shannon, do you want to unmute yourself and ask your question?
Sure. I thought it was a really cool presentation, really enjoyed it. I'm not that familiar with the lattice Boltzmann method, more like finite differences in finite volumes. So this is just solving like the shallow water equations in one dimension, right?
Yeah. Lattice Boltzmann works. Lattice Boltzmann is one-dimensional. Yeah. Sorry.
Okay. Like, you know, when you're doing hydraulic modeling, you sometimes use you often use the cross section, like the other direction in your model. Could you use this method in that direction as well, if that makes sense?
Yeah, I can. I have actually I can actually adapt this method to give a three-dimensional bed as well, which I am going to I'm going to make that slightly better before I show it to people, but it does do that as well. Yes.
Cool. Thank you.
Okay, yeah, Killian, you say there was another question from the Learning Studio.
Hi there, it's John Shiak from Manchester Metropolitan University. Thank you for your presentation. That was really enjoyable. Like with Shannon said, I'm not too familiar with the lattice Boltzmann technique. Can you include bread friction terms in the model? Just that might also have an effect on the fluid flow.
Yes, so the lattice Boltzmann has a built-in scheme. This is actually what I did my undergraduate dissertation in project in. The lattice Boltzmann has a built-in term called the force term, and that in itself encapsulates all of those things. The the friction of the bed itself to the water, the gravitational rotation of the earth, everything that can affect the fluid flow in an external way is incorporated in this one term, which is a pretty big term. It's a pretty long piece of code to get that particular term to work. But yes, that the lattice Boltzmann method automatically incorporates that in, and that can be adjusted depending on what you would want to do, and that is going to be something I'm going to have to look further into when I want to incorporate more sediment flow into the fluid, because that would change the way the force term is acting on the fluid.
Thank you.
Thank you, Elysia. Thank you, John. I think we probably have time for one more question. If anybody would like to put their last question in the chat window, or you can unmute yourself if you want to speak to Elysia.
Okay, that last question raised another question from me, Paul Kimber. Is it possible to run this software, I'll call it the other way around? One of the interesting things might be, can you shape the bottom of a river or a channel to optimize the flow rate, or conversely, to minimize the flow rate? Are there any structured bottom surfaces that would help either to maximize the flow of water or minimize it?
That's actually very good. Yeah, I think there are ways that the lattice Boltzmann method could be altered to do that. The lattice Boltzmann method is a pretty flexible method, with a lot of it being quite easily molded. For instance, you can shape the riverbed in any way you want. The boundaries of the riverbed, because it has an elastic collision scheme, bounce back.
Yeah.
You can shape the riverbed. You can add objects in. You can have objects flying, floating, embedded into the ground. And the lattice Boltzmann method is very, very good at doing the flow around that, where other methods are a bit faulty when the flow is strongly three-dimensional. So there are possibly ways that could happen. I don't know currently, because I haven't looked into that specific question, but that is very interesting. So I will look into that, because that has piqued my interest quite a bit.
Okay, thank you.
Okay, thank you, Paul. But we're now quickly approaching 6 o'clock. So I suppose, Elysia, you could answer one more quick question. So has anybody else got any quick questions? We are going to the Revolution Bar for 6:30. If anyone would like to join us, if you're in, Manchester near Oxford Road.
In the chat, Stephen. I think it's from Shannon. Could I
Oh,
share my?
Shannon.
Yeah, I can share my email address. That's fine. I think it's on the IMA website. Let me just check.
Yeah.
It definitely is, because I'm a member of the Northwest Branch Committee. So if you look at the committee, I'm on there, and I think it would have my email address. But
you
I'm
can
fairly sure.
Elysia, you can just put your email address now in the chat window, because I'm sure lots of people will want to email you after this talk. So Elysia will put her email address in the chat window, so you can easily contact her. So yeah, Elysia, did you talk about journal paper? You said when were you
sorry,
get a journal paper written by?
Yes, I'm hoping to publish a paper with the conference I'm attending in April, this coming April in Japan. But by the end of this, by the end of the second year of my PhD, I'm hoping to be publishing a paper in a journal as well. Hopefully, water journal.
Okay, thank you, Elysia. Okay, everybody, thank you.